Hello students, welcome to EPG Pathshala. I am Dr. Dinesh Kalyansundaram from IIT Delhi. Today we are going to talk on Laplace transforms. To understand mathematical need for Laplace transform, mathematical formulation and its properties, and the applications of Laplace transform to solve differential equations. These are the three objectives of our today's class. Today we are going to see what is Laplace transform, when and why should we use it, and how to solve differential equation using Laplace transform with some solved problems. Laplace was a great mathematician and astronomer. He gave this famous integral called Laplace transform. Initially it was used in probability theory. Then later other genius mathematicians such as Petrova, Grothendieck, Lagrange, they all used these transforms, and they have given the present look of the current Laplace transform. Laplace transform is useful to solve ordinary linear differential equations with constant coefficients. It can transform a difficult problem, that is a differential equation, into a simpler one. What is a simpler one? An algebraic equation. So that is the key importance of Laplace transform. In other words, it transforms a problem from one space, that is time space, into another space, that is frequency space. For example, suppose we are going through a maze. So we are seeing at the front view. So this is one space. So to solve a maze, it would be easier for us to look from the top view. Then we can easily solve the problem. So seeing it from a different space can make a complicated problem into a simple problem, and that is what exactly we are going to see. From front view, if we change to top view, or from time space we change to a frequency space. From differential equation we change to algebraic equation. So this is the transformation, and that is why the word transform comes into the game. When and why to use it? Imagine there are two different people from different countries and different languages. Let's say there is a speaker and there is a listener. For them to understand, there is an intermediator who converts the language of the speaker into the language of the listener so the listener can understand. So there is a difficult to understand language, and the intermediator conveys the same information in an easy language. Similarly, Laplace transform acts as an intermediator. A differential equation, which is a difficult problem, is converted into a much simpler algebraic equation using a mathematical tool, and that mathematical tool is the Laplace transform. When and why to use Laplace transform? Let us assume there is a problem which is changing in time space. That means it is a function of time. So the left box that you see, the problem in space where one needs complex operation mathematics like multiplication, division, etc. to solve. Then you apply a Laplace transform. Now our problem is converted into a space where one needs only simple operation like addition and subtraction to solve it. Now the problem from time domain has been now converted into frequency domain. After you are satisfied with all the addition, multiplication and stuff, now you come to a certain value, but that value is in frequency domain. For the real world to understand, we have to come back to time domain so that it will make sense for a common man. So what we do, we apply a inverse transformation, which is the inverse Laplace transform. Now once we apply the inverse Laplace transform, which is a one-on-one mapping, that if you select this, then this should be the inverse transform there, which is what we are going to see later. Then once you apply that inverse transform, you are going to get the solution of the problem with respect to the original space. So therefore the solution is going to be again back in time space. Let us see an example. Let us see how to solve a bigger mathematical problem like a large computation or multiplication. Let us say 15 625 into 625. How can we do this multiplication? It's going to be time taking. One easy way is to write the same in terms of powers. For example, 15 625 can be written as 5 power 6 and 625 can be written as 5 power 4. Then 6 plus 4, we can just add it, 5 raised to the power 10. Now this has been, which was a complicated multiplication problem, has been converted into a simple addition problem. Now what we have to do? We have to take an inverse of 5 power 10. How can we take a 5 power 10 inverse? It is better that we refer to a table which is all the powers of 5 written down. Yes, mathematically it would take you the same time, but let us assume you already did a chart where you can refer to and make it, because not always you are writing an exam. Sometimes when you are working, you need to do things faster, and sometimes when the computers are working, instead of multiplying 15 625 into 625, a computer can always easily refer to a table and do that. So if you are in in terms of bioinformatics, or when you are in high computational fields, we want to always reduce the computational time. So what we do, we take we go from one platform or one space to another space, and then we have some charts to see the correlation. Once we have a correlation, we just bring it back to the original space. Now 5 power 10, if you look at the chart, then you might just find out that the value is 9765625. Let us compare between a D operator, which is the conventional method to solve a differential equation, and Laplace transform. Conventional D operator method. Let us say you have to solve the equation, which is y double dash plus y dash minus 2y is equal to 0 with a boundary condition y of 0 is equal to 4 and y dash of 0 is equal to minus 5. The moment you specify of 0 of something, then it becomes the initial condition. So they have given the function value y at let's say some space time is equal to 0, it's 4, and the gradient, which is y dash of 0 is equal to minus 5. Then these becomes the initial value problem. Now how do we do a conventional D operator? We represent y dash as d and y double dash as d squared. So what do we get? We get d squared plus d minus 2 whole times y is equal to 0. Then what do we do second? We form the characteristics equation by substituting m in place of d. So we have m squared plus m minus 2 is equal to 0. Conventional D operator method, continuing from the previous slide. So the roots of the equation are m1 is equal to 1 and m2 is equal to minus 2. We go to step 4. The solution is going to be y is equal to c1 times e power minus m1x, which is 1x, plus c2 times e to the power of m2x, which is minus 2x. Then what we are going to do in step 5 is apply the boundary conditions. Y of 0, that is y at x is equal to 0 or time t is equal to 0, and y dash of x is equal to 0 or time t is equal to 0. We are going to apply the boundary conditions into the equation y is equal to c1 into e power x plus c2 times e to the power of minus 2x, and y dash you can find out from this. Then we can apply the values. We solve the two equations, then we'll get two unknowns are there, C1 and C2. When you solve the equations, you will get C1 and C2. Then we have to just simply write the step 6, which is the final solution as shown in the slide. Laplace transform method. Let us see how we can do the same differential equation solution using Laplace transform method. The step 1 is we take Laplace on the whole equation. L of y double dash plus L of y dash minus L of 2y is equal to L of 0. L of double dash can be written as s squared y of s, capital Y of s, minus s into y of 0 minus y dash of 0. Then L of y dash, the second term, can be written as s times capital Y of s minus small y times 0, that is function of 0, or time t is equal to 0, minus the third term. The third term is Laplace of 2y. 2y Laplace is equal to 2 is taken out as it is a constant into capital Y of s. Then Laplace of 0 is 0. Then what we do is, you can already see it is an easy algebraic equation. Now we can solve for y of s. In step 2, y of s will be equal to, you take the unknown terms to the right hand side, 4s minus 1 divided by s squared plus s minus 2. We are continuing the Laplace transform method from the previous slide. So once we have the equation, we are going to check whether that form of equation is available in the standard table or not. If it is in the standard table, we can just get the solution. If not, we are going to write it in terms of simpler terms. Okay. So 4s minus 1 divided by s minus 1 into s plus 2, which is can be again written as 1 divided by s minus 1 is one term plus 3 divided by s plus 2. They are all equal. So now if you go and compare the graph, whether such a data is available in simple format, it will be readily available. If it is readily available, compare the chart and then straight away write the equation. So 1 divided by s minus 1, the Laplace inverse transform is just e power x. So then 3 divided by s plus 2 is just 3 is a constant, so you take it out, then s minus of minus 2. So anything 1 divided by s minus any number will be equal to the solution inverse is or the inverse solution is e power minus that particular value times x. So here it's s minus of minus 2, so it's going to be 3 times e power minus 2x. So the complete solution is sum of the individual solutions. What is a mathematical definition of Laplace transform? The Laplace transform of a function or signal f of t is defined as: first multiply the given function with e power minus st, then integrate the product by applying the limit 0 to infinity. Please remember that Laplace transform is always in the positive zone. That means time can only be positive. So always Laplace is 0 to infinity. This is a key difference between Laplace and Fourier transforms, which we are going to see later. The integral is termed as a Laplace transform. L of f of t, that is, you are applying Laplace on a function f of t, okay, which is equal to 0 to infinity, that is where we integrate function f of t times e power minus st dt. Okay, the common notations is capital F of s if the function is, you are calling the function as small f. If you are calling the function as small g, then it is written as capital G of s. Understanding the Laplace operation. What happens when you multiply something by e power minus st and integrate the product? What is the effect of multiplication? At time t is equal to 0, e power minus st is equal to 1. As t tends to infinity, that means it keeps on going, then e power minus st is a decaying exponential function, and then it goes to 0. So by multiplying f of t with e power minus st, we are basically applying the weight. So e power minus st is the weight of the function. So we are giving more weightage to the function close to time t is equal to 0, maybe few numbers. But if the time is going to be too far away, we are not going to consider, right? This is like you giving weightage to your friends or even your father's promises. When it is going to be done in the next few hours or next few days, you will give more importance. But if it is going to be done, let's say 100 years from today, 300 years from today, you are not going to give any weightage, any importance, right? So you are basically, in your heart, you are doing something like a multiplying with e power minus st. Now what is the integration effect? That is the second part of the game. When we integrate the product, it will generate cumulative. What does integration means? Adding up. You are integrating, you are summing up. Okay, so it will sum up all the things that you are going to do in this whole time. Okay, so that will tends to converge. Okay, because as time is equal, when the time t tends to go to infinity, e power minus st is 0. So anything much far away from today, you are not going to consider, and you are going to integrate what you are going to do from today or from now till some finite time. Okay, and that is up to which is going to depend on the function f of t. The effect of multiplication by e power minus st and integration of the product. We are going to see some graphical examples. Let us take a function t squared. Okay, the function is t squared. Okay, you can all do this by opening an Excel sheet and doing as follows. You can take time t is equal to 1, 0, 2, 3, 4, 5 up to long values, maybe 100, 200. Then you can calculate the t squared. Then you will see the second column, t squared values. Then what you can do is e power of minus st. You can assume s is just 1 or something, because it's just a constant, any constant s. So for now you can just assume 1. Then you can just see the values of e power minus st, and you can see after time t is equal to 16, at which e power minus st is 0.002, then it becomes at 17 time it becomes 0.001, and afterwards it's just decreasing, and after 20th it is 0.000 some number, which is, since we have only put 3 decimal places, we are only seeing 3 decimal numbers, but after that it is going to become very negligible. Now let's do multiplying f of t into e power minus st. Then you can see those values. Then let us say we are integrating. That means the first term is getting added to the second term and then goes to the second. Okay, up to the n terms you are going to add. For example, we take point number time t is equal to 2. We know f of t into e power minus st is 1.801. So what you have to do is you have to add 1.801 to 0.67 and plus 0. So that will get you have to add to the previous values, right? 0.671 is the previous value and 0 is the first value. So you have to add that to 1.8. So what you will get 2.473. Now similarly for t is equal to 3, you have to do 2.721 plus 1.8 plus 0.67, then you will get 5.194. Similarly, if you do for everything, at every time you have to add to the previous sum. So the easiest way is, for example, let's say time t is equal to 12, you are getting 1.203 for f of t into e power minus st. Okay, I hope you are all following. So this integral product is just going to be, you can see the integration up to time t is equal to 11, which is 26.371. It is given in the fourth column. You can just add 1.203 to that, you will get 27.573. I hope you are all clear. Now if you keep adding, now if you see, after time t is equal to 19, it just still remains at 31. So that means it is getting saturated. It just converges to 31. Let us see the example. Let us see the graph on the right side to understand it better. We see the function f of t is increasing, which is given by the brown dots. It keeps on increasing, right? Now what we can do is, if you take the Laplace transform, which is the blue line, you can see it just increases slightly up to maybe the value 10 or 11 or maybe 12, and then it just keeps on going for a fixed value. So what we are trying to do is, we are capturing the property of the function and then stocking it up into the first few terms. So we know what's a pattern just by seeing at the few terms, and then so we don't have to do it for a longer time. And that's the effect of integration after we multiply by e power minus st. We are going to graphically see more how it is different. What I have done is, on the graph, I have just made the y-axis in logarithmic scale so that you can see. Otherwise, it's not very clear. Now we are seeing a violet line. What that is f of t into e power minus st. How does e power minus st look like? It looks like a straight line in a logarithmic scale, but it may look like a decaying line in a normal scale. You can plot that e power minus st since you have that graph also. Now when you multiply with the function f of t into e power minus st, you see the violet line. Then when you take the Laplace transform, you see it becomes converging to a constant fixed value. We are going to see the effect of multiplication and integration of the product, and this is example number 2. What we are going to do is, we are going to take the same t squared and see what will happen if we make the t squared into, we square it. That means we make it t power 4. How is it going to change? Okay, so when you do the same steps as I told you before, you get time t, you open an Excel sheet, make time t scale, then t power 4 function, then e power minus st, then f of t into e power minus st, and then you integrate the product. Now we are going to the next slide to understand it more. We are going to see graphically and numerically how it is very different. As you can see, after time t is equal to 39, the value starts converging to the value 2379 point something. When the function was t squared, it was converging around 1920. Now it is converging around 40 and 45. And again you can see the different graphs and how the blue curve converges to a fixed value. So the message is, irrespective of the function and the value, maybe the time until that particular finite integration is going to change. However, we are still able to capture the properties. That is the message from the 2 examples. Let us see Laplace transform of some key useful functions. Let us assume the f of t is 1, and you can do the same thing for any f of t which is a constant. So Laplace of 1 is equal to 0 to integral infinity e power minus st into dt, and when you integrate minus st dt, you will get minus of e power minus st divided by s applied evaluated between at value 0 and infinity. So infinity is the first term, then we subtract the when the value 0 is applied. You can see the Laplace of 1 is equal to 1 over s, s being greater than 0. Please remember the time is always greater than 0. Similarly, if there is a constant f of t is equal to k, then Laplace of the function is just going to be k over s for any s greater than 0. We are going to see another function which is e power at, where a is a positive real constant. This is an exponentially increasing function as shown in the figure, where the brown curve is increasing as time t is equal to greater than 0. You should always see the function which is greater than 0. We have just shown the value is increasing from the minus terms. Okay. Then L of e power at is integral 0 to infinity e power minus st into e power of at dt. So we can write, we can sum the terms inside, so we can write it as minus of s minus a times t dt. So once you apply the integration, it will become minus s minus 1 by s minus a is going to be outside. Then you will get e power of minus of s minus a times t applied between 0 to infinity. When you apply the limits, the conditions, you will get e power of at is equal to 1 by s minus a. S is greater than a. Let us see a function which is sine of at. You know, sinusoidally it is going to change, and that is shown in the graph on the right side. Now Laplace of sine of at is going to be a little difficult and cumbersome, but let's just go through that process. We have e power minus st into sine of at dt integrated from 0 to infinity, and the way we are going to do it is we are going to use the uv dv method. So I will let you figure that out, and then you will get minus of e power minus st cos of at divided by a, applied limits between infinity to 0 or 0 to infinity, minus s by a integral 0 to infinity e power of minus st cos of at dt. Okay, then we are going to again apply the uv integral method. So that is going to become, so once you get cos, then you're going to get another sine. We already have another sine for which we need to find the integration. So what you can do is we can take the sine again. Okay, so you will get 1 by a minus s squared by a squared f of s will be equal to f of s. So you will be equal to f of s. Okay, so then f of s, whatever it is, you can sum it up. Then you will get then you can take it back. So therefore f of s will be equal to a divided by s squared plus a squared, s greater than 0. So to really understand how we are doing the integration, you have to use the uv method. Okay, so I will let you try the first step, and always remember to practice it. Just don't see the slides, it's not a movie. You have to practice it to get to it. Okay, I have given all the intermediate steps. Find out how each step you can go through, then you will end up with f of s is equal to a divided by s squared plus a squared, s greater than 0. Limitations of Laplace transform. It is always important to understand the limitations. It is completely not advisable to use a formula without understanding its limitations, and that is the problem of the current generation of students. The first limitation is that Laplace transform can be used to solve for linear differential equation only with constant coefficients. You cannot use them to find general solutions, and it is suitable for initial value problems with initial conditions. What is the initial value problem? When the time t is equal to 0, if the value of the function is known. or the value of the slope or the gradient of the function is known. What do you mean by gradient and slope? That is the differential, first differential. For example, if f of t is the function or the solution, and we know f of t at time t is equal to 0 is equal to c1, that it's a particular value c1 given, and that's the initial value of the function, and initial value of the slope or the gradient of the function is f dash of t at time t is equal to 0, then that is the initial value of the slope or the gradient or the derivative, and that is a constant c2. So if we know these, then these become the initial value problem. So we are going to see some solved problem examples to understand this. Before we go into jump into that, we need to know what is the general procedure for approaching such a problem. Solving differential equation with constant coefficient, and this is one of the most important applications of Laplace transform. I am repeating this so that it stays in your thought always. Okay. The general procedure is first convert the differential equation into algebraic equation, and we are going to see how, and then solve the algebraic equation, then try to express the unknown function as a sum of the first and second order terms, then use the inverse Laplace transform to obtain the solution to the original problem. And these are the ways we are going to approach the whole problem. We are going to see the Laplace transforms of very commonly used functions. The f of t is the common functions, and L of f of t is the Laplace transform. You can refer to these tables for the common functions. We are continuing other common functions, and the table shows the key important functions. Properties of Laplace transform. So we need to understand how we have to shift time and frequency and how it's going to affect the equations, and these are going to be just thumb rules for how we can change. The frequency shift. Frequency shift can be done. Let's say we have a function f of t and the frequency has to be changed, then how it is going to affect. So that is equivalent to multiplying the time f of t by into a function e power minus at. So once you do the operations as shown, e power minus at f of t, then you multiply it e power minus st dt and integrate from 0 to infinity. Then you can actually add the minus st and minus at, and it becomes f of s plus a. Now that's the frequency shift. What is a time shift? A time shift meaning you shift time t with a constant a. How does it change? Okay, so the Laplace of f of t minus a will be equal to f integral f t minus a e power of minus st dt integrated between 0 to infinity. Now this is a little bit tricky, where you have to apply x as t minus a, then you have to find dx, then you have to find as t tends to a, x tends to 0, and as t tends to infinity, x tends to infinity. So when you apply the integral, then you can find out L of f of t minus a will be equal to e power of minus as, okay, which will become a constant times f of s. Properties of Laplace transform. We are going to do frequency shift on cos omega t, which is the function f of t. So f of s is equal to s divided by s squared plus omega squared, and f of s plus a is equal to s plus a divided by s plus a whole squared plus omega squared. So therefore L of e power of minus at cos omega t is equal to s plus a divided by s plus a whole squared plus omega squared. Properties of Laplace transform. Time differentiation. If L of f of t is f of s, then we want to show then the Laplace of differential of f of t with respect to time t is equal to s into f of s minus the function of time at time t is equal to 0 minus f of t at time t is equal to 0. This is a very important first step to solve differential equations. So what we are trying to say is the Laplace of the differential is equal to s times Laplace minus the initial value of the function at time t is equal to 0. So let's integrate it by parts. Okay, let's assume u is equal to e power minus st and du is equal to minus s e power minus st dt, right. So if you differentiate u, you will end up getting du, which is minus s times e power minus st into dt, and v is f of t, so that dv is equal to differential of f of t by dt over into dt. So this is the parts we are going to integrate by parts. Okay, so you have u, you have du, you have v, and we have dv. Properties of Laplace transform, time differentiation. Making the previous substitution gives L of df over dt is equal to f of t into e power of minus st, substituting the values infinity and then subtracting it from 0 when the values are substituted as 0, minus integral 0 to infinity f of t into minus s times e power of minus st dt. So basically what we are doing is the uv integral. So we are separating out the integrations. That is equal to 0 minus f of t at time t is equal to 0, or you can say f of 0 plus s times integral 0 to infinity f of t into e power of minus st dt. So we have shown that L of df of t is equal to s times capital F of s minus f of t at time t is equal to 0. What we are going to see here is how to extend the result which what we have learned before. That means we want to do L of the second differential, Laplace of the second differential, and L of the third differential, nth differential. So that is going to be just s square times, let's say second differential is equal to Laplace of second differential is equal to s square times f of s minus s into f of s at time t is equal to 0 minus f dash of t time is equal to 0, and you have to just continue it. Time integration property, L of an integral, that means the function is under integration and you are taking a Laplace. So that will be basically as shown by L is equal to 0 to infinity times, you just write the whole function inside it, multiply by e power minus st dt. Now we can integrate by parts. Assume u is equal to something and du will be equal to f of t dt. Am I right? Because we are taking the integral. And dv is equal to e power minus st dt. And if you take dv as e power minus st dt, v is equal to minus 1 by s e power minus st and dt. So this is the integration by parts, and this is what you should have applied in the previous few slides. If you don't recognize that, then maybe you can see that. So what we are trying to see is any function, okay, where uv is there, where there are two terms, then what we can do is d of uv will always equal to u times dv plus v times du. Okay, then you can find the, if you know one of the terms, you can find the other term. Okay, I will let you go and find out what it is. Now when you go to the next slide, you can see this example how it is solved, and you can solve the other examples. Then we make these substitutions, how we can integrate it by parts. Then when you apply it, you will find out that it will be equal to 1 by s times f of s. I am purposefully not telling every point in the equation and the solution. I want you to go and try and then come to this last solution 1 by s f of. We can see a transform pair between f of t and capital F of s, and depending on what equation you need, you can use as appropriate. Laplace transforms and inverse Laplace transforms are linear. That means L of any constant multiplied with f of t, and then there is another function g of t when it's added. You can write it as individual functions, individual Laplaces, then multiplied by respective constants. Okay, and the same thing applicable to Laplace inverse. An important point to remember: there is always a pair. The function f of t, when you apply a Laplace transform L, it becomes capital F of s. And then when you apply a reverse transform or an inverse transform, L inverse, then that capital F of s should always become equal to f of t. So it's a very closed loop. That means the energy or the function is never lost. This is a very key step. If you make a Laplace transform, just to cross check at any point, if you think your differentiation or your addition or multiplication something is not right, you always take an inverse Laplace transform and see if it is coming back to the original point. Okay, so in that way we are always conserving the energy. The above statement makes it as a pair. That means f of t has a relationship L with respect to f of s. Now this is a pair. What that means is for each f of t, there is a unique capital F of s. Okay, which means they are husband and wife. It's a unique pair for which each f of s there is a unique f of t. There is an inverse relation also. Okay, it's a one-on-one mapping. Solve the differential equation with a given condition, initial boundary conditions. Like we said, we always need initial boundary conditions for Laplace transform. Okay, the step 1 is to convert into algebraic equation, right? X double dot is as same as x double dash, and then you can substitute x squared minus x of s, then so on. Then x dot is equal to x dash, then you can similarly substitute. If you keep on substituting, then you solve for x of s, and finally you will come to 1 by s times s squared plus 4s plus 3. We are going to see the step 3 and step 4. Step 3 is, now you have this whole complicated function. Now you have to write in terms of partial function. That means there should be only one s in every separated function. That should be the goal. Now we can write it in terms of, let us assume, right, a over s of s plus b over s plus 3 plus c over s plus 1. Why we are writing s plus 3 and s plus 1? Because if you multiply s plus 1 into s plus 3, you will get s squared plus 4s plus 3. That's why. And the third term, a over that small s, is a term which is outside. Now you can multiply them. Now you will get s squared plus bs times plus cs times something, which will be equal to 1. Now you can compare the coefficients of s squared on left hand side versus right hand side. In the left hand side you have as squared plus bs squared plus cs squared is equal to 0. Then you can compare the coefficient of s. Then you can compare the coefficient of constants. Then you can find all the values. Now in the fourth step, what you have to do is just put the values of a, b and c, and you take the inverse Laplace transform, and then there you go, the solution. So students, let us summarize what we have learned in this module. Laplace transform is a useful mathematical model. Why? Because it converts a complex problem in a time space to a simple problem in a frequency space. Or let us broadly understand, it can convert from one space to another space, where we can just do simple algebraic modulations then take an inverse Laplace transform and come back to it. In other words, it is as simple as we taking a simple problem, let us say 1024 into 1024. Now, how would you solve the problem? It's easier to write the problem as 2 raised to the power 10 into 2 raised to the power 10. Now, what does that give you? It's just a simple addition of the powers. So, you will get 2 raised to the power 20. You can always look at the graph or a chart where different powers of 2 is written, then refer to it and come back and write what is 2 raised to the power 20 mean. And that is the same way we are doing this problem. We elevate the problem to a different space, then you can do just addition, and then you just look at a table and come back to the original solution or the solution that we want. Okay. The most important usefulness of the transformation is that we have to see how we can solve, or we can use the same concept to solve differential equations. And again, the important key factor is this can be used only to solve equations with constant coefficients. Then what we can do is the properties of Laplace transform is used to solve ordinary differential equation.